All right, we are working in section 5.2, which has to do with different types of bisectors and triangles. So yesterday in 5.1, we worked with perpendicular bisectors and angle bisectors, but this time we're going to be using those in triangles. So there's a couple points of vocabulary that we have to hit first, and then I'll show you how to do it. I've got a nice example of how to do this as well. So if you need graph paper, that would be pretty helpful to do that one on. So that's just a suggestion to help keep you neat. Anyways, concurrent means it's when three lines or more intersect, they're considered concurrent. So when you have three or more lines intersecting, they're concurrent. So it's tough to give it a description without getting too confusing, but if you use it in that sort of sentence, it makes a little bit of sense. Again, when three lines intersect, they're concurrent. So where they intersect is that point of concurrency. So that's the intersection, and that's a point of concurrent lines. So to give you an example, just to draw a picture, if you have three lines like this that intersect, that right there is the point of concurrency. Now we care about where those happen in actual triangles. So one of the points that we care about that actually becomes pretty helpful is a circumcenter. It sounds kind of weird, but a circumcenter is essentially the intersection of three perpendicular bisectors in a triangle. So we're going to call it a point of concurrency. Again, that's just an intersection where three or more lines meet. So it's the point of concurrency of the three perpendicular bisectors in any triangle. So to give you an idea of what that looks like, I can draw it here on the left. If I just take a triangle, regular old triangle that looks like this. Now I'll do the three perpendicular bisectors in different colors. And so I'll do the first one in red. I'll cut this line right here. So I made it perpendicular to the bottom part. And again, it's got to be a bisector. So it's got to cut those in half. If I do another one in green, I'm going to do the one on the left. So in order to make it perpendicular, it's got to kind of cut and make a sort of angle, and it's got to be in the middle here. Now that, if I just extended the line, would go something like this, and it would go out in that direction. And if I do the last one in blue, then, and I do this other line, the middle is about there, and then if I draw a line through that, it looks like this right here is my circumcenter. So the circumcenter has one important property, which is why we care about it. So the big star you want to put down underneath that is that it's equidistant. Remember that word from yesterday, equidistant, from the triangle's vertices. Oops. So from the triangle's vertices. So what that means is, for that triangle over there, I'll give it some letters. It means the circumcenter is equidistant from points A and B and C. If I drew them in, it would be kind of tough to see. Maybe I'll draw them in and then erase them after. I'll do them here in yellow. Basically, it's saying that this distance and this distance and this distance are all the same. It's equidistant to the edges. So here, let me do that again so you can see it. It's equidistant from the edges. So if that was confusing, how I drew it, you might just want to rewind, a minute and see if it makes sense the second time through. But a circumcenter, all it is it's a point of concurrency of three perpendicular bisectors in a triangle. And when I drew it, I kind of just eyeballed it, so it's never going to be perfect. But you can calculate that point. And again, the reason that we care about it is that it is equidistant from the triangle's vertices. So if you have any 3 points and you want to get exactly in the middle and be equal distances, you can do that. All right. So the three different kinds of triangles, acute triangles, right triangles, and obtuse triangles, the circumcenter can happen at a few different points. And so the one that I drew up here, the purple triangle that you guys are looking at up here, that is an acute triangle. So you'll notice it kind of looks like this, where the circumcenter happens inside the triangle. So again, remember that property that equal distance from the edges is really why this is useful. But yeah, so those are three perpendicular bisectors. And you can see that, yeah, they're right in the middle and they bisect it, and also that there's a right angle there. In an obtuse triangle, the circumcenter happens outside the triangle. There's no point inside the triangle at which it's equal distance to the vertices, so that's why. And then in a right triangle, it's right on the edge. So it's always going to occur on the hypotenuse. It's just how it works out. So just something to make note of and something that you might get asked about. But I want to show you guys how to actually find one. So if you know how to find a perpendicular bisector, which you do, I mean, we did it in class. So I'm looking at it right now, and we did this today or yesterday or whenever it was. So you've done that before. So finding more than one of them shouldn't be a big deal. So I've got one here. Again, graph paper would be a good idea. I've got the answer in the top right corner if you want to try it out before I do it. But I'll go through and show you how. So I always find it easier to get a picture. If you try and do this without one, it's going to be really annoying. So again, just get a picture. So 0, 0 is here. 4, 8 is around there. And then 8, 0. 8, 1, 2, 3, 4, 5, 6, 7, 8, 0. Yeah, so this is your triangle. And I do need to label these points because, like, it's just going to make it easier for you. So I'm going to call that A, I'm going to call this B, and then I'll call this C. So again, if we need to find the circumcenter of this triangle, we have to find some perpendicular bisectors. Now you know that the circumcenter is just the intersection of three perpendicular bisectors. So you don't actually have to find all three. You can just do two of them. You could find all three, but I don't know why you would. It's just easier to find two of them. So in this case, there's one that's easier than the other ones. I don't know if you can tell, but the easiest one to draw in is this one here. So you can tell that it's exactly halfway between. That's at the point 0, 4. Or sorry, 4, 0. So that's exactly in the middle. So you should be able to know that from algebra 1, this is the line x equals 4. X equals lines are vertical lines, and y equals lines are horizontal lines. So that's something that I think that you should know already. So you've already got one of the lines. So perpendicular bisector, number 1 would be x equals 4. So if you wanted to get one of the other ones, this is a little bit harder. So you have to do the same kind of process that we did in 5.1. You have to, and I'll do it in a different color so that you can tell which word goes with what. So I might as well just do the one that's here, and I'll draw it in. It's going to be something like that. So in order to get this perpendicular bisector, it's going to be an equation of a line. It's not just a vertical line like the x equals line was. It's something that's got a slope. It's got a y-intercept, so it's a little bit harder to find. So I should be able to get the slope by using the slope from AB, and actually the midpoint too, because I need a point and a slope. I need a point and a slope to make a line. So my point is right here, and my slope is just going to be the perpendicular slope to AB. So the slope of AB, I should be able to find pretty easily. It's just 8 minus 0, 4 minus 0. That slope is 2. So the slope of something that's perpendicular to AB, that should be -1/2 because it's the negative reciprocal. So I said I needed to get my point and my slope. I've gotten the point. No, I've gotten the slope. What am I doing? So I've got that. Now I just need to find the point. So that should be this midpoint. So in order to find that, you just average the x's and the y's. So a and b would just be 0 plus 4 over 2, and then the y would be 0 plus 8 over 2. So that midpoint is 2, 4. Okay. So in order to create that line, I'm going to use this slope and this point. So I'm just going to do it over here. That means that's y equals mx plus b. If I substitute everything in, I've got 4 for the y. I've got negative 1/2 for the slope. And then for the x, I have 2. So I've used all 3 pieces of that. And then plus b. So 4 equals negative 1 plus b. And then that means b equals 5. So you've got y equals negative 1/2 x plus 5. That might have been a little fast for you, so if you had a hard time with it, you pause it, look at what happened, rewind, go back and watch that part again because it's not easy. But, I mean, that is all Algebra 1. I haven't done anything, you know, the only geometry I've done is midpoint, I think. Everything else is Algebra 1. Now, you could go find the third bisector, but you don't really need to because, again, I'm trying to find the point of concurrency up in this triangle, trying to find that circumcenter up there. So I just need to know when the green line, I need to know when this red line, x equals 4, intersects this green line right here. So it's just a system of equations. You have 2 equations and 2 variables. So I should be able to combine them. Since I know that x equals 4, and I also know y equals negative 1/2 x plus 5, the easiest thing to do is just take the 4 and substitute it in for the x. So y is negative 1/2 times 4 plus b, which is negative, oh wait, b. Oh, I didn't fill my 5. Sorry. That's a 5, sure. So negative 1/2 times the 4 plus 5, which is y equals negative 2 plus 5, which is 3. Looking good. So that means the y is 3, and I already know that the x is 4. So it looks like my answer should be the coordinate 4, 3. So that's your circumcenter. So yeah, it's a lot of work. I mean, you have to find perpendicular bisectors and use a whole crap ton of algebra. I mean, it's not the easiest thing in the world, but keep in mind that if you wanted to, and I'm going to draw on the triangle again, you could have used this perpendicular bisector as well. It's a pretty terrible drawing, but you get the idea. You could have used that perpendicular bisector as well. And if you use the black one and the green one, it may be a little bit harder. You might have to solve a system using elimination or something. But if there's a vertical or horizontal one, always use that. So if you found this difficult and you know that you need to see another example, I am going to put another one at the end of the video. So, you know, you can stay tuned and you can watch that. I'll just pause for a second. All right, so there's one other type of point of concurrency in triangles that we have to go over. That's in-center. So I've got that. I've got some properties about in-center down here. And then I've got to show you about some circle stuff that happens. So an in-center is actually a little bit easier. So that's the point of concurrency of the 3 angle bisectors in a triangle. So again, this one has another property that's kind of useful, and I'll show you guys that after I draw it. But if I draw a triangle, so 3 angle bisectors, I'll do them in 3 different colors so you can see. It's not going to be perfect, but that would be 1 angle bisector. This would be another angle bisector. That's terrible. All right, this would be another angle bisector. I should do another. And then the last one would be up here or something. So you've got that. So that's an in-center right there. So the one property about an in-center that's useful is if, you know, the circumcenter was equidistant from the vertices, the in-center is equidistant from the sides. But it's not just anywhere. I mean, you have to go the shortest distance to the side because, I mean, realistically, you could go from the in-center to the sides like anywhere on the triangle. I mean, I could go here or here or here or here or here. I mean, there's a million different places that you could go, but you don't need to do that. So the in-center just works with, you do the shortest distance, which always makes a right angle. It's one of the things that we learned. So the shortest distance from a point to the side makes a right angle. And if you do that to all 3 sides, I'm just eyeballing this, by the way, I'm not like perfect, but those three yellow segments are going to be equal to each other. And so those yellow segments are what this is, that it's equidistant from the sides. So it's really tough to calculate the incenter without like advanced trigonometry. So we're not going to do that. But you do have to know, one, what an incenter is. Two, you should be able to draw it. And three, you should know that it's equidistant from the sides. So that's the one important property that you want to know about it. Now, the circumcenter can happen in the triangle, on the triangle, or outside the triangle, but the incenter is always going to be on the inside. And so I've got a couple pictures here so you can see that whether it's an acute triangle, like it is on this one, that it's going to be on the inside. You've got the obtuse triangle, it's on the inside, and then even on a right triangle, it's in the middle. So if you're going to be equidistant from the sides, you have to be inside the triangle. There's just no way that it won't work out that way. So the other triangles to even draw that in, so this is equidistant from the sides, this is equidistant from the sides. I'm trying to draw these at right angles the best I can. And then this is equidistant from the sides here. So that's an incenter. So what you see here is pretty much all you need to know. So there's a couple other vocab words here that have to do with circumcenter and incenter. One that, another useful thing about the circumcenter, so I got to draw one first. So if I draw this, the circumcenter is the center of the circle that you can draw around the triangle. So that sounds a little weird, but if you drew, I'm going to try and draw this with the circle thing because I'm really bad. So if I take a circle and I touch all the sides of the triangle, imagine that sort of touches all the sides. Yeah, that works. The center of that circle is the circumcenter, which is kind of a cool thing. So if you ever need to find the center of a circle, you can actually just use a triangle instead if you need to, and we'll use this again in chapter 10 or 11 when we get to circles. So the center of a circumscribed circle, so circumscribed circle is the circumcenter. So again, a circumscribed circle is a circle that touches the three vertices of a triangle. And the center of that circle is going to be the circumcenter. So if you have a circle and you know 3 points on that circle anywhere, so it could be a circle that you do on a map somewhere, in an ocean somewhere, anything. But if you draw the 3 points and you want to know where the center of that circle is, that's also the circumcenter. So that's one thing. So almost the opposite is true with an incenter. An inscribed circle is a circle that touches all the sides of a triangle. So to make that happen, it has to happen on the inside. So inscribed circles happen on the inside. If I draw another one here, and you take a circle and you put it on the inside, it's almost there. And you touch all the sides to see if you can see that it's going to touch there, it's going to touch there, it's going to touch there. The inside of that circle, that's the incenter. So the incenter is the center of an inscribed circle. So you'll see some applications of this as we move forward, and we've got a couple days in class to practice, but I wanted to at least show you guys this so you've seen it. So that covers everything that you need to know to be able to do any of the practice. So I promised under 20 minutes, and I did. So, however, I am going to do one more example of circumcenter for those of you who had a hard time with it. Typically, it's something that's a little bit tough. So if you want to see this example done out, I am going to do it now. So that way you have it. So it's going to be the same kind of steps as the other one. I've got the answer up there. This one is actually it's going to turn out to be a right triangle. So it's going to happen right on the edge. So it should work out similar to the one that we did before. So I've got 0, 0 here. It's actually only in the first quadrant, so I don't even need this much space. I actually should probably move this over a little bit. So I've got this. So 0, 0, I've got 0, 12, 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12. So somewhere up there, and then 6, 6. 1, 2, 3, 4, 5, 6. So it's something like this. The drawing isn't perfect, but we'll get that. So if you draw it in, you should be able to tell that there's one that goes through this way. And again, I know that it goes through there because I'm drawing it through the middle and I'm making it at a right angle. If I drew the other two, one of them would be here. Oops, that's not right. Let's try that again. I'm going to draw something like this. And then something maybe like this. So it's a little tough to draw. So you might have drawn it yourself and it doesn't look like it intersects at this point here, but it actually does. So that's why drawing it, it gives you a good idea, but like calculating it mathematically actually gives you the exact answer. So we'll go from here. So the purple line is the easiest one to find. Again, this one I trust that you know from Algebra 1. That's y equals halfway between 0 and 12. I mean, that point is 0, 12. So halfway to 12 is 6. So that's the line y equals 6. So you can find any one of the two red perpendicular bisectors. It really doesn't matter which one you find. So I guess I'll just do this bottom one. So I'm going to find this perpendicular bisector here. So I'll color the other one in like a different color. That way we don't get confused about which one's which. So I'm going to find the red one. So again, in order to find this, I need a point and I need a slope in order to find the equation of that line. So the point that is on that, I know right now, is 0, 6. I can tell because that's the, wait, it's not 0, 6, sorry. I'm looking at the circumcenter already. So the point that's going to be on that line is this midpoint. Now that's halfway between, again, see, this is why we label points, because I've got no idea what's what. A, B, C. So I need the midpoint of AC, which is going to be the average of A and C. So that should be 0 plus 6 over 2, 0 plus 6 over 2, which is 3, 3. I also need a slope for that. So the slope of AC, at least, is going to be, I think the slope's just 1, because 6 minus 0 over 6 minus 0 equals 1, which means the slope that's perpendicular to AC should be the negative reciprocal, which should be -1. From there, I should be able to substitute my slope and my point into the equation of a line. Again, I've got a point here that I know is on this perpendicular bisector. It's that red midpoint. And then I've got a slope because I know it's perpendicular to AC. So when I substitute those into an equation, I should be able to do, y equals mx plus b, which means y equals mx plus b. So 3 equals -3 plus b, which means b equals 0. So that means y equals -x. So that's the equation of that line. -x plus 0, but you can just call it -x. So I've got -x, and I've got y equals 6, which makes sense based on the graph that I have up there. So I need to find the intersection of y equals 6 and y equals -x. So if I just take that and plug it in, I'll plug it in a second. All right, so I had to pause it because somebody else is here with me and they caught a mistake that I made. I don't know if you guys caught it as well, but it's good to mention. So here, when I was solving for this b, right here in this step, you can see that I really should have added 3 to both sides. So let me just scroll down so I don't just scrunch this on the bottom of the screen. Realistically, since that's -3, I should be adding 3 to both sides after that, and I should be getting b equals 6. So let's fix what I did. So that should be 6. So that means my y should be equal to -x plus 6. So that isn't correct. My bad. So I'll fix that up here as well. And, no harm, no foul. We'll finish the question. So now I've got y equals -x plus 6 and y equals 6. When I substitute those in for each other, I take this y equals 6 and I can plug it in for y. So 6 equals negative x plus 6. And this is the one that's going to come out to be 0, because when you subtract 6 from both sides, you get negative x equals 0. And, I mean, it's pretty apparent, but for those of you who don't see it, yeah, x equals 0. I know that x equals 0, and I know that y equals 6. So that means my circumcenter in this case would be 0, 6. Based on the graph, you can see that. I mean, it is right there. It's at 0, 6. My picture described it, and yours might have been close, but you can see mathematically that that's where it should be. But yeah. Anyways, cool. So I hope this helped. Enjoy, and I will see you guys later.